Let's consider the problem 1325E, Ehab's real number theory problem. In this problem, we're given an array of length n. Each element in the array has at most 7 divisors, and this is important. Our goal is to find the length of the shortest non-empty subsequence of the array whose product of the elements is a perfect square. And the subsequence doesn't have to be continuous. So for example, in the first sample input, we can just take the number 1 or the number 4. That's of length 1 and it's a perfect square. The second sample input, we can take both the 6's. That's of length 2 and it's a perfect square. In the third sample input, we have to take the whole thing to get a perfect square. And that works because 6 is 2 times 3, 15 is 3 times 5, and 10 is 2 times 5. So we get 2 times 3 times 5 squared. In the fourth sample input, there is nothing that we can make. There is no subsequence. We get -1. And note, just to reiterate, just because in these samples they're all continuous subsequences, it doesn't mean they have to be. Okay, let's consider what we can do with the fact that every element in the array has at most 7 divisors. So if every element has at most 7 divisors, then let's count the number of possible prime divisors. Okay, let's just pick small prime divisors for sake of example, but there's really no reason they specifically need to be small prime divisors. Let's say we pick the prime divisors 2, 3, and 5. Now, then the smallest the number can be is 2 times 3 times 5 is 30. Okay, how many divisors does 30 have? Well, 30's divisors are 1, 2, 3, 5, 6, 10, 15, and 30. Let's just shift this over so it's not so crammed into the end. Okay, so how many divisors is this? Well, this is 1, 2, 3, 4, 5, 6, 7, 8 divisors. And in the problem, it specifically tells us each element has at most 7 divisors. Right? So whatever our 3 prime divisors are, it'll always be the case that that if there's 3 prime divisors, then there'll be more than 7 divisors. Right? And this is because if we look at this in a little more detail, each of the prime divisors has one corresponding value that needs to be multiplied to get to the result, and then you have 1 and the value. That's a total of 8. So this tells us that there can be at most 2 prime divisors for each integer. Okay, this means that if we prime factorize it, we will get 2 prime divisors. So if we go back to the sample input, one of the sample inputs is 6, 15, and 10. So 6 gives us 2 times 3, 15 gives us 3 times 5, and 10 gives us 2 times 5. Now, this would still work if these are raised to a power or something, right? And there may not be, right, x that way, and there may not be, depending on the value of x, there may be more than 7 divisors, but let's not worry about that. Let's just use the fact that there are most 2 prime divisors. So for every value, a of I in the input, we'll just find all the prime divisors. And this can be done in square root of a of I time. And a of I is at most 10 to the 6. So in O of square root 10 to the power 6 time, and again, 10 to the power 6 is the value of a of I, the max value of a of I, we can find all the 2 prime factors. Okay, so we prime factorize a number, right? Once we prime factorize a number, and I'll tell you why the 5 to the x doesn't matter. So because once we prime factorize a number, let's say we have a number that is 2 to the power a times 3 to the power, not 3, let's pick like 7 to the power b. Okay, we only want to figure out the smallest subsequence of numbers that will the perfect square. So let's just say a here equals 7 and b here equals 2. Well, if b equals 2, then we can simply just remove this. We can remove this term because it's an even product, so it's a square. And 2 to the 7 can be converted to 2 to the 1. So if it's an even, we can just remove it because it's already a perfect square. If it's an odd, we can remove 2 to the 6 because that's a perfect square. So we're left with every number is a product of, or can be reduced to a product of two numbers, right? So what this means is, even if we had, instead of 6, we had 2 to the 3 times 3, right? 24. Well, 24 can still be converted into 2 times 3 because we can take out the 2 to the 2 because that's a perfect square. So every number, we've converted it into two numbers, right? A times b. It doesn't matter that 2 times 3 does not equal 24, it's converted into 2 times 3. Okay, what do we do if there's only one prime factor? Well, in that case, we can use 1, right? So we can let the number 5 equals 1 times 5. What if there's 0 prime factor? What if we just have 1? Well, if we just have 1, then this number in itself is a perfect square. So then we can just output a sequence of length 1. And again, if we had 4 equals 2 squared, this would be converted into 1, and we'll just output 1. And to reiterate the point, if we had 20 equals 2 squared times 5, this also gets converted into 5 times 1. So in this case, we don't have to consider it because then we already have the answer. So for all other cases, we have a product of two values. Okay, what do we do with this product of two values? Well, we can build a graph. So up there we had 2 times 3. So we'll have a node 2 and a node 3, and we'll draw an edge between them. We had 3 times 5 and 2 times 5. So we have a node 5. So we have 3 times 5, so there's an edge. We have 2 times 5, so there's an edge. We have 5 times 1. So there's an edge there. This is not the sample. We've added in the 5 times 1 from the sample, but that's okay. Okay, now consider any cycle in this graph, right? In this graph there's only one cycle, but consider a cycle. Well, a cycle goes into every node once in the cycle, right? It goes into the node once and it comes out of it once. That means there are two edges attached to that node. If there's two edges attached to that node, then that means that if we just label this, right, this edge is 6, this edge is 15, this edge is 10, because 2 times 3 is 6, so we get 6, 3 times 5 is 15, and 2 times 5 is 10. So that's the value that created that edge. So for every cycle, if we multiply all those values in the cycle, then we get a perfect square. Because, well, we're multiplying 5 twice, 2 twice, and 3 twice. So the length of the cycle is the minimum subsequence size. This means that to solve the problem of finding the minimum subsequence size, we have to find the smallest possible length of a cycle. Okay, let's consider, in an ordinary graph, what is the smallest possible length of a cycle? Well, in a normal graph, we can solve this in O of n squared. And the way we do this is we pick a node to start out with, right? So let's just say we start at the node 2. And then we build a tree, a DFS tree of this whole thing, or BFS tree, sorry. So 2 goes to 3 and 5 in depth 1, and then 1 in depth 2. And then we draw in all the extra edges. So there's an edge between 3 and 5, which is like a back edge type. Okay, so oops. So what does this give us? because it's a DFS tree, we know the distances to this is 1, 1, 2, and 0. So for every back edge like this, a possible cycle length is 1 plus 1 plus 1 for this extra edge here. So our cycle length would be 3 here because there's no other back edges. This is how we do it for the value 2 as the root, right? But this only works if 2 is in the cycle. And note that that's because the back edges are like the path that they represent is this path here. From the root down to the left node, through the back edge, not the back edge, through the cross edge, down to the right node, back up to the root, right? The root has to be part of the cycle. And since we don't know that 2 is part of the cycle, let's just say we would have tried 1, which is not part of the cycle, right? So we have to try every edge as our starting edge. And for every edge as our starting edge, we have to build this BFS tree and try all the back edges. And so, we have n starting edges, or starting nodes, sorry. And for each of these, we have to do an O of n. So it makes O of n squared. And as n is, the number of nodes here is really big, this is not possible. Each element has up to 7 divisors, and there are 10 to the 5 elements. So 7 times 10 to the 5 is the number of nodes. And, well, it's slightly less than that, but it's still too big to do n squared. Okay, let's consider how to fix this. So note that we had to try every element as our starting edge because we don't know what element is guaranteed to be inside the cycle. But what if I told you we have some information about which element is guaranteed to be in the cycle? Then you would have some more, then you'd be able to do this better. So let's consider the case where we have 6, 10, and 15 from the sample, right? This is 2 times 3, this is 2 times 5, and this is 3 times 5. Okay, the square root of 15 is less than 4. So this means, I argue, that one of the elements in the cycle has to be less than 4. And here's why. Because we've already guaranteed that there's no subsequence of length 1. If so, that means one of the values is a perfect square. We would have taken care of that up here. We would have factorized to 1. So this means the sequence has to be of length at least 2. And if it's at length at least 2, then that means there is at least one value that is less than equal to the square root of the biggest value, right? One of the prime values is less than equal to the square root of the biggest value. And this is the case because you cannot have two values greater than the square root of max AI, right? Let's just say you have x comma y is greater than the square root of max AI. Well, this means that x times y is greater than AI, the max AI. Well, let's write max up here. X times y is greater than the max AI. And that's not possible because, it has to equal to the max AI. Or some of the smaller AIs too, right? It has to, the values x and y that you take, like all the edges, all the nodes that you take with the prime values, well, their product has to be a perfect square, but each value x and y for one edge, right? There has to be one edge, or for every edge, if the two nodes on the left and the right side are x and y. These are the two nodes on the left and the right side, right? So one example on this edge is that, like, this could be here x and this could be y. Or this could be x and this could be y. But it is not possible that this is y. This is not the case because we are looking at one edge, right? So if I take this edge, then we could have this is x and this is y. Okay, so if the product has to equal to the value that creates the edge. And if the product is greater than the maximum AI, then it cannot equal to the product that makes the edge. So we know that one of the values is less than or equal to the square root of max AI. Okay, we can use this here. We can use this, so this means that how many possible values are there for the starting node? Well, we know that one of these values, one of the nodes with a value less than or equal to the square root of max AI, is guaranteed to be in the cycle. So now we have square root of AI starting nodes, because one of these is guaranteed to be in the cycle. And it doesn't matter which node you start with. Uh, if this node you start with is in the cycle, then you will find the cycle, regardless of where you start. Okay, so this is 10 to the power 3. For each of these 10 to the power 3, we have to look through the whole graph to make this BFS tree here. So we have a 10 to the 3 times n solution. And just to be clear where the 10 to the 3 comes from, we have a square root of n times root AI solution. And this runs in time because n is 10 to the 5 and square root AI is 10 to the 3. This is 10 to the 8. This does run in time. Okay, let's consider the code for this problem. So max n is 10 to the 5. And I use this value for the nodes, the number of nodes too, like the prime nodes in the graph. And this is because the number of prime values less than or equal to 10 to the 6 is less than or equal to 10 to the 5. Infinity is 10 to the 9 just because that fits cleanly into an integer. Okay, so I have my int n, I have my input array AI. We'll just ignore the rest of the answers for now, the rest of the variables for now. So actually let's keep track of good. So remember how we said that one of the values is less than max AI, square root of max AI. Well, we need to know what square root of max AI is. So good just keeps track of that. At first, good is the maximum value. So good is the max of all AIs, and then we just take the square root of that. And we can round down, that's fine. It's not an issue. Because it has to be less than equal to the square root, which is less than the square, like, if we round down, it's still less than equal to the square root. If we round up, then it's strictly less than. But this is fine. Okay, so then for every integer n, we let x equal AI. And this is just the way I had coded it. You can use AI directly, you don't need to copy it into x. So we need to find all the prime factors. So we start from j is 2 and we go up to square root of x. And this is because if x can factor to two values, one of those two values will be less than or equal to the square root of x. So we count how many times we're using this value, and this is so that we know if it's an odd number of times or an even. So while x is divisible by j, we divide x by j and we say we've divided once. Okay, if we divide it an odd number of times, like 1, 3, 5, then we take out the even. So we take out, if it's 5, we take out 4 of those. We only leave 1. So one of the prime factors is j, in this case. So now that we went through, we got all the prime factors. Okay, what happens if we got no prime factors? Well, if x equals 1, and again, this could also mean that you have, like, say, 2 to the 2 times 3 to the 3, right? If this happens, it'll be empty because it doesn't take an even one. Those are perfect squares and it just tosses them out. They're irrelevant because we're only looking for perfect squares, and so we can take out all the perfect squares taken care of in one value. So if x equals 1, we have a perfect square, so we output 1 and we return. We're done with our program. If it's not the case, then we don't have a perfect square. So we add x to one of the factors. And let's just say we have the value 2, right? This is something that would happen. Like, or if we have a prime value remaining, then x would not be 1. And it has to be prime, because if it was divisible, then we would have gotten another value in here. It wouldn't have ended that loop. Oh yeah, it's also okay that we're reducing x and still using square root of x, because it doesn't matter what x started out as. If x starts at like 50 and we divide it by 2, and x is 25, well then there has to be a factor less than or equal to 5. Doesn't matter what we started out as, because the same rule applies for the smaller x. Okay, so yeah, if we have a prime, we're left with a prime value of x. We add it as a prime factor, and then if val.size equals 1, this just means that there's only one value in vals. So it could be because of this. It could be because only one prime value was found here or whatnot. If there's only one value, we add the value 1. So like if there's only 5 in there, we make it 5 times 1, or 2 times 1. And this is so that we have exactly 2 in vals.size. Okay, now let's look at this next thing here. Oh yeah, so vals was a vector int array. For every a of I, it stores the 2 values that factorize it. Okay, let's look at this map here, index. So it takes in a value and it gives it an index, and it takes in like the prime values or 1, right? So it's taken 5 to say, okay, that has the index of 0. Then it takes in 3, that has an index of 4. Then it takes in 2, that has the index of 2. It takes in 7, index 3. It takes in 1, index 4. It just keeps doing that, and add keeps track of whatever index it's at. So add starts at 0. So for every element in vals, if we have not yet assigned it an index, then we assign it an index on the map. So the index of whatever the value is equals whatever is next. So if the first one's 3, it'll be 0. Next one's 2, it's 1. And then we increment at. Now this thing in the middle is start is simply a vector. So what this says is if j is less than good, this means that j is less than the square root of the max ai, less than or equal to the square root of the max ai. So it's a possible starting element. If it's a possible starting element, well, then we're going to push back the index of the possible starting element. Keep in mind that j is now an index. The index of j, that is the node number. So index of j is the node number we're giving it. So we have to push back at, because that is the node number of j. Okay, so now we know that both the 2 prime values of vals I have a node number. If it didn't have one, we added. If it already had one, we just didn't do anything. So now adjacency is an array of vectors where for every element in the adjacency array, it stores all its neighbors. So adjacency takes in the index of the node, right? So it won't take in the value of j, it'll take an index of j. Take in the index and it will connect it to the other nodes, node numbers. So adjacency, index of vals I0. So again, we want to connect vals I0 to vals I1, right? That'll make this edge from up here. I'm trying to make all these edges. And so we're trying to connect the vals I0 to vals I1, but we connect index of vals I0 to index of vals I1 because index is the number of the node, right? So the node numbers, we might label this 0, we'll label this 1, label this 2, it's an ugly 2, and we'll label this 3, and that's the index. So the way we store it is we're connecting 0 to 1 with 2, 2 to 3. And that's because you might have a really big prime number that's close to 10 to the power 6, and we don't want to make an array that big. We want to make it 10 to the power 5. This is probably not necessary. You could probably have an array of size 10 to the power 6, but then you would need to do something clever about making sure that when you loop through the whole entire graph, you don't look at those. But that's actually very easily doable. You probably don't need to do all this stuff that I'm doing to keep track of this. That's just how I did it. Okay. So then we look at for every starting node. The starting nodes are the ones less than or equal to the square root of max ai. And this just means that that one of these starting nodes is guaranteed to be in the middle of the cycle. So we originally set our answer to infinity. That's the smallest cycle length. The smallest and the maximum answer would have to be is n, which is 10 to the 5. Infinity is greater than that, so this is a fine thing to do. Distance keeps track of each node's distance from the root. So distance would be like these red values here. 0, 1, 1, and 2. That would be distance. Visited is if we visited an element in the array. Next one, so this is a queue. So we're going to do a BFS, right? So when we do a BFS, we're keeping track of the distance from the root, and the current node that we're at, and the parent. And that's written as a small comment here. Okay, for every starting node, we're first going to set the visited array to all to false. The first item we're adding to it is, well, the distance is 0, the node is j, and we're going to set the parent as j. It just comes from itself, and that's fine. Okay, so when we're in the loop, the first thing we do is to read the distance, the node, and the parent, and then we pop it. If we've already visited the node, we don't do anything. If we have not visited, then we say we marked it as visited, and we set the distance of the node equal to d. Now note that I don't need to reset the distance array, and that's because I can just reset the visited array. Okay, now the skip thing here is also something that could be done a little simpler than the way I did it. I didn't realize that until later again. So, what you want to, the case this is trying to account for is the case where you have a node, where you have two values of a and I that connect the same node. So let's just say you have 2 and 3. If you have two edges between them, then your answer is 2. Now this you can simply check for in your adjacency array. I, however, did not do that. I did a different thing, and I realized later that there was this easier solution than I'm just telling you. So what I did was, I said, actually, let me get back to skip in a second. Let's first explain this loop. So for everything that adjacency x is connected to, for all its neighbors, if the node is not the parent, and ignore skip, if we have not visited the node, then what we'll do is we'll add it to our queue. So the distance is distance plus 1, and the new node is I, that's the one we're connected to, and the parent is x. Now if we have visited the node, then we're going to update the answer. So we're going to say it's the min of distance I plus distance x plus 1. If we move up to, you know what, let's just move this graph here over. Okay, so if we move to this here, what it basically happens is if we've already visited I, right? So let's just say that this is like all the 0 and the 1 we visited because they're marked in red. That's the 2 and 3 nodes, and then the other ones we have not. So when we visit this, we mark it as 1. Well, then we say that we've already visited through this edge here. This means that it's a cross edge or a back edge, but we'll come to the back edge thing in a second. So if it's a cross edge, then, well, the cross edge to the root and to the node form a cycle. And so we can, that's what this is doing here. It's taking into account the cycle. The cycle length is distance I, and distance I is this distance here. Give it a second to update, sorry, okay, cool. Plus distance x. Distance x is this distance here, plus 1, and that's the extra edge that you're drawing. That's a possible thing that we update our answer with. Okay, however, just because we see another edge, it could be this cross edge here, or it could literally be the edge you're coming right back off. Sorry, it's lagging a little bit. Yeah, cool. It could be that edge that you're coming right back of. And if that's the case, to avoid this, what we do is we say if I is not equal to P. This makes sure that you're not going right back up to your parent. This does allow you, however, if you have something like 1, 2, 3, and you have an edge that goes here, it allows this, it allows this edge that goes from 3 to 1 to count, right? It only makes sure you don't go right back up on the edge you came down, and that you don't want to do. But this edge here, you want to be allowed to take, because that represents this cycle here. Okay, so that's all good. Now what is the skip thing? Well, let's say that between 2 and 3 there's 2 edges. Oh, let's put this in green actually. So if there's 2 edges between 2 and 3, then when I mark the distances, I go 0, 1, 2. I don't want to go back up this edge, but I want to go back up this edge to find the cycle of length 2. And I told you an easier way to find cycles of length 2, but this is just the way that I happen to be doing it. And so the first time you find an edge back up to your parent, you skip it. The skip starts as false. The first time you find an edge back to your parent, skip is false, and you skip it, so you don't do this visited thing. However, you then mark skip to be true, which means the next time you find the second edge, you find the second edge up to your parents, skip is true. So this does activate, and it allows you to find the cycle of length 2. Now granted, the cycle will only be correct in the answer when one of these 2 nodes here is the root, but we'll guarantee that one of these 2 will eventually be the root because of our list of starting nodes. Right? One of them has to have a value less than or equal to square root of max AI. Okay, so then we just repeat this whole loop for every single starting node, and we output our answer. And if our answer is infinity, that means we haven't found a potential cycle, so we just output -1. This is how you solve this problem.